I should also apologize a bit because my talk is not very specific to periodically driven systems. It's more about a general framework for dynamics of disordered interacting quantum many-body systems, including periodically driven systems. And okay, good, that's up. And in my defense, I'll say that whatever numerical results I show, they have all been obtained for a periodically. Okay. All the numerical results I'll show have been derived for a periodically driven, have been obtained for a periodically driven system. But that was more for convenience rather than there being anything sort of very fundamentally important with periodically driven systems in what we do. So this work was done sort of primarily by a student, by a PhD student just starting his PhD, Vikram over here, who is also in the audience. And that's important because if there are questions, if they're easy ones, I'll answer them. If they're not, then I'll direct them to Vikram and I'll cite interest of time. And this is the reference of this work. Okay, so just to sort of set up the stage, basically the dynamics or the dynamical phase diagram of disordered interacting quantum many-body systems has been sort of on our minds in various forms and various shapes for quite a bit of time now. And basically what we want to understand is that if we take an isolated quantum system, which is interacting and which is disordered, then how does its dynamics look like? And there are a lot of questions here. I mean, of course, one expects that when the disorder is very weak, there's a bird in here, okay, not bad. Okay, so if the disorder is very weak, then you get into an ergodic phase. The system behaves like a diffusive metal. But the real sort of interesting questions start when you start cranking up the disorder. And of course, there is one question that has been sort of bothering many of us for a long, long time. Or when I say long, long time, I mean over the last few years, is this question that whether there is indeed a sharp phase transition in a thermodynamically large system from an ergodic or sort of a slightly modified rest ergodic phase to a genuinely many-body localized phase. And of course, you know, there is some amount of progress in 1D. In higher dimensions, it's still a completely open field as far as I'm concerned. And then there are questions about the existence of that phase, about the critical disorder for some standard models. And of course, if that phase exists, then there are also questions about what is the nature of that phase, how important are the many-body resonances or the many-body versions of Mott resonances that you would see in an otherwise non-interacting Anderson localized system. And one of the questions that has been addressed more recently is whether these resonances can actually give rise to a very sort of parametrically large pre-thermal regime, which precedes a possibly genuine phase transition. And much of what we have seen in numerical calculations so far, whether that's basically, there are questions about whether that is genuinely an MBL phase or whether that's basically a very long pre-thermal phase. Of course, some other questions that have been addressed for a bit longer have been at even weaker disorders where basically, at least again from some numerical and phenomenological ideas, we have observed or argued for the presence of so-called slow dynamics. And by slow dynamics, I mean that, for example, if you have some conserved quantity that does not undergo diffusion, instead it undergoes subdiffusion, and the eigenstate expectation values satisfy some slightly modified version of the eigenstate thermalization hypothesis. But of course, there are again questions that whether this is this phenomena that we see, whether it's basically just a transient, eventually for a very large system at some large time scale, eventually giving way to diffusion, or whether this subdiffusive behavior is there to stay. I mean, there are questions about that. Arguments in favor of this kind of subdiffusive slow dynamics have ranged from, you know, possibly that the physics is dominated by Rayleigh-Griffiths regions. I mean, Sarang here has worked a lot on that. But of course, they also raise some questions about what happens to these phenomena then in higher dimensional systems, or for example, in quasi-periodic systems where you still have some rare region effects, but not because of there being rare fluctuations in the disorder potential. There they come from the initial conditions and so on. But sort of what I want to convey from this slide is that there are lots of very interesting questions generally about the dynamics of disordered interacting quantum many-body systems, which still sort of continue to bother us, even though we have been studying this for quite a while. unfortunately, I'm not going to answer any of these questions because these are all very difficult questions. Instead, what I am trying to do is try to sort of convey to you a possible way, or it's at least as far as I am concerned, it's sort of a first step towards possibly building an analytic theory for computing these local observables in these kinds of parameter regimes, which are sort of ergodic, but not sort of conventionally ergodic, and possibly extend them later to check whether the MBL phase exists or not. So the kind of setting that I have in mind is some sort of a spin system, and this is your spin chain. But I want to look at the state or the dynamics of the state first in the many body Hilbert space, and that's kind of at least that's one can argue that that's in fact quite a natural thing to do, because as soon as you write down the state on a piece of paper or you write down the state on a computer, you basically are writing down a vector which lives in this many body Hilbert space. Now, of course, it's a bit of a scary thing because the Hilbert space is very complex and correlated. And to start with, the size of the Hilbert space, actually the dimension grows exponentially with the system size. The connectivity is extensive in system size typically, and for long range systems, it could be faster than linear. These are sort of scaling issues. There are more fundamental issues, such as the matrix elements that you see in, there could be matrix elements between different states on the Hilbert space, or there could be on-site potentials on the Hilbert space, which are going to be very, very strongly correlated. And that's not a big surprise, because in order to specify the Hamiltonian, you only need order or polynomially in the system size number of energy scales, random or otherwise. But you are actually assigning an exponentially large number of energy scales when you write down the Hamiltonian on the Hilbert space. It's not surprising that these matrix elements are very strongly correlated. And then sort of the last killer is the fact that this kind of a Hilbert space, when you sort of try to write down the adjacency matrix given a Hamiltonian or some generator of the dynamics, this basically has loops at all length scales. And that basically means that this kind of a Hilbert space graph is very different from a conventional Cayley tree or a Bethe lattice or a random regular graph, where loops are typically very, or in trees they're absent, in random regular graphs they are very long. So that also sort of throws away some of the ideas that you might have hoped to borrow from existing literature on that. So, but nevertheless, let's recognize these difficulties and try to push ahead. And again, the setting that I will have in mind is that I'll start with the setting of something which is very similar to a quantum quench, which is I'll start with a very simple spin configuration, which basically means that that state on the Hilbert space is localized on one particular basis state. And as time evolves, we know that these spins are going to scramble. They are going to develop possibly long-range entanglement. And what that implies on the Hilbert space is that this is going to sort of spread out. The amplitudes of the state on this Hilbert space graph are going to spread out in time, possibly in a very complicated fashion. So what we want to do or in this talk is to sort of build a very specific and concrete bridge between observables that you can compute in the real space language and correlation functions that you can compute on the Hilbert space. Now, you might ask that why do I want to do this? Why do I actually want to go to a seemingly much more complicated setting? The reason is that in real space, while it's while real space correlations are definite observables and of interest, possibly accessible in experiments also, it's very difficult to actually do a microscopic analytical theory starting from the real space, simply because the Hamiltonian is interacting and disordered and far out of equilibrium. On the other hand, on the Hilbert space graph, even though the graph is complicated, which is basically the sort of red/yellow flag here, you can nevertheless say that, well, it is actually the dynamics of a single fictitious particle on this complicated graph. And that doesn't, when you phrase it in that way, it doesn't sound too bad, because we actually have some experience in dealing with dynamics and localization of single particles on very high dimensional graphs. At least there is some technology that can be developed and possibly taken forward to include the complications that come with this graph being the Hilbert space graph of some locally interacting many body system. So basically, and this is something Vikram and I are doing parallelly, which is to develop some analytical ways of computing correlation functions out of equilibrium on the Hilbert space graph. And the idea would be to rely on them and then use this bridge that I'm going to construct in this talk to eventually come up with an analytical theory for the real space correlations. Okay, so that's basically the plan. And to make this sharper, let's actually define the kind. I've been keep saying dynamical correlations. Let's actually sort of give them some identity. So in real space, what we would be interested in is the spin autocorrelation, which typically looks like this. Now, as I said, I'm going to work with periodically driven systems for practical purposes. So there is no energy resolution. There are no issues with mobility edges and all those kinds of things. So I can basically close my eyes and take infinite temperature traces wherever I need. So that's my infinite temperature spin autocorrelation function. And that's possibly the simplest dynamical correlation you can compute in real space. And then you go to the Hilbert space and ask that what is the simplest dynamical correlation you can compute therein. And that simply happens to be the return probability, which is basically asking that if I start off from a particular state, let it evolve in time, then what is the probability that at some later time t, I find the system or this fictitious particle in the same state. And the main aim of this talk would be to develop a relation between the C of t and this return probability R of t. So before I get there, let me say a few words about return probability, because possibly the spin autocorrelation is something that many of us have thought about long, so I don't want to say much about it. But I would like to point out a few specific things about the return probability that's relevant for a many body system. So the first thing is that the return probability itself does not actually admit a well-defined thermodynamic limit, because for any finite t, it's always exponentially small in system size. So if you take the thermodynamic limit, then for any finite t, you will find that the return probability is 0. And this is independent of which phase I am in. This is simply due to the fact that the Hilbert space graph has an extensive connectivity. So as soon as you start doing some dynamics, there are order L channels through which probability can escape a given state. So one actually has to look, and this is sort of a numerical evidence for this here. What I have done is I've computed return probability for some non-integrable, or not I, but Vikram and Kritika calculated the return probability for a non-integrable spin chain for a decent range of system sizes. And you can see that for any time that you see, the return probability goes down with system size. On the other hand, if you, I'm not showing the plot for the rescaled version, but you can believe me that if you take the rescale, or I shouldn't say the rescaled version, but if I take the return probability and exponentiate it, raise it to a power 1 by L, that actually admits a well-defined thermodynamic limit. So that tells me that it's RT to the power 1 by L that I should be looking at. Okay, but that brings in another small complication. Oh, before that, I should mention that again, this is a signature. The fact that this is exponentially small in system size for any t is that the graph is very different from a random regular graph, because I pulled out this plot for the return probability for a random regular graph, and you can see that all the modulo trivial finite size effects here, the data is converged for all possible system sizes. Okay, but as I said, trying to look at RT to the power 1 by L or return probability in a many body system brings in another small complication, which is in the infinite time limit, the return probability actually becomes the IPR of the system. Okay, and that's again something one can show by algebra. And we know that the IPR again, scales as the Hilbert space dimension to some power, which is negative, and between magnitude is between 0 and 1. So the issue now is that if I actually raise the return probability to the power to 1 by L and take the t going to infinity limit, then I actually end up with a constant. So if I take the return probability, raise it to the power 1 by L, I'll basically get e to the power minus d log 2, which is a finite number. So RT to the power 1 by L, what it does is it decays and then saturates to a finite value, even in the thermodynamic limit. It doesn't drop down to 0. So that tells me that it's not the actual decay of the return probability that contains quote unquote universal information. It's how it actually approaches its infinite time saturation. That is what one should be looking at. So the appropriate quantity will be of the form, either you take R of t over R of infinity and then take a log, divide by 1 by L, or you simply raise the quantities to the power 1 by L and take ratios and do whatever you want. Okay, there were 3 hands. So
what is that capital D?
D is some number which is between 0 and 1. It's basically
It's not
the
the dimension of
fractal,
the Hilbert space. It's not the dimension of the Hilbert space.
No. So NH is the dimension of the Hilbert space. D is the fractal exponent. Saranganemos, yeah. Yeah, so we didn't see any difference in any initial state. I mean, of course, we are taking a locally interacting system, but it doesn't have any symmetries. It doesn't have any extra structure, like there is no U1 conservation and so on. So in a way, on the Hilbert space graph, all the many body states have the same connectivity, or the connectivity scales in the same way. So there is no difference. Yeah, so it's independent of initial condition. No initial condition is special. Oh, so of course, so you can argue that this saturation is indeed non-analytic across the MBL transition. And in fact, the most recent numeric suggests that the fractal exponent is actually discontinuous across the MBL transition. But I'll keep myself in the ergodic phase for this talk. I'll not venture into the transition. Okay, but you're right. But the point is that whatever you do, it's really not the decay, it's not the decay over here that you should be interested in. It's this saturation or approach to saturation that you should be interested in, no matter which phase you're in. That's the only point I'm making. Okay. So with that piece, armed with that piece of information, let me sketch how we actually go from the spin autocorrelation to the return probability. Okay. So this derivation will proceed in 2 steps. So the first step would be to relate this spin autocorrelation to the spread of the wave function on the Hilbert space. And that will involve the non-local Hilbert space correlators and the notion of a distance on the Hilbert space graph. And the second step would be that we will use the conservation of probability on the Hilbert space and use that to deduce something about the morphology of the propagators and come back to return probability. Okay, so to start with, we need a notion of distance on the Hilbert space graph. And because we are dealing with spin systems, the Hamming distance is really a very convenient choice. It's really the number of spins, which is different between 2 configurations. Formally, I can, of course, write it in this way, where this notation means that, so this S can take values +1 or -1, +1 for spin up and -1 for spin down. I is the Hilbert space basis state I'm looking at, and the little I is the site that I'm looking at. So basically, I take 2 configurations, I and J. I subtract the spins at the same real space site. I sum them up. I square them so that it's 1 or 0, and then I sum it up. So that basically gives me the Hamming distance. And the nice thing is that you see this notion of Hamming distance already brings in the product of the spin expectation values at 2 configurations. And you can already see why this might be useful to connect it to the real space autocorrelation. Another thing I would like to point out is that the number of states at any distance is basically L choose R, but that's again, simply a property of the graph, nothing to do with the details of the system. Okay. Then the next thing we need to do is to define a non-local Hilbert space propagator, which has this notion of distance in it. So that's again very simple to define. We say that we start with some state J. We evolve. We look at the weight on some state I, which is at a distance R, and then I sum over all possible such configurations which are at the same distance R from my initial configuration, and then I average over all possible initial conditions. So really, this propagator G of R comma T, it's not really a propagator. It's basically amplitude square of some propagator, which is the total probability that I find the state at distance R on the Hilbert space at some time t. Okay, so then the next step is to understand or realize that I can think of this G of R comma T as a genuine probability distribution on the Hilbert space graph, because each element of G of R comma T is positive, and they sum up to 1 simply because of conservation. So What that means is I can actually define the first moment of this propagator. I keep calling it a propagator, but you know what I mean. I can define the first moment, which basically gives me the effective size of the wave packet on the Hilbert space graph. And that really quantifies the spread of the wave function on the Hilbert space graph. And then I use this relation between the Hamming distance R or the fact that the Hamming distance R is trivially related to the product of spin expectation values. You do the algebra, and what you find is that the spin autocorrelation is very trivially related to the Hilbert space spread as 1 minus 2 times the spread over L. Okay, and that sort of is the flow chart. You define a notion of distance, you define a non-local propagator based on that distance, and then you define the spread, and from there you see that the spread is very trivially related to that spin autocorrelation. Okay, so far so good. Now, having related this autocorrelation to the spread, we somehow need to come back to return probability. Now, in order to do that, we will need to understand the morphology of this G of R comma T on the Hilbert space graph. Now, there are a couple of things to note here. The first thing is that for however large my system be, as soon as I switch on the dynamics for any finite t, my C of t is necessarily less than 1. And this is a strict inequality. Okay, if this has to be a strict inequality, what that means is that the average spread at any finite time should actually be extensive in system size. Otherwise, in the limit of L going to infinity, C of t will remain 1 for a finite amount of time, which basically is not possible. So that tells me that for any finite t, R of t is order L. And again, this actually goes back to the fact that I actually have extensive connectivity on my graph. More importantly, what I next do is I write my propagator as the number of states at distance r, which is nr, which was L choose r, times some average weight at distance r. Now, this in principle is a function of r, t, and the system size. But note that I can actually write this nr in this fashion. I can take the Gaussian approximation for the binomial, and this actually begins to have something which looks like a large deviation form. Now, if this is true, and I need to have R of t, which is, and I need to have R of t, which is order L, that suggests that my average weight should also have a large deviation form, and it should be a function of x, where x is simply R over L. So the overall picture that emerges is that n of r is sharply peaked at r equal to L by 2 or R over L equal to a half. And this is a function which in general decays with the distance. But because this should have a large deviation form, this will together give me a g, which is sort of peaked somewhere in between 0 and half as far as x is concerned. So that is the crucial sort of physical import of this picture, that this average weight actually has this large deviation type structure. Okay, and then what I do is I split this function capital F of x comma t into two parts. That's just a choice for convenience. You don't really have to do this, but I split it up into two parts. One is g of t, which has the behavior at x equal to 0, and then the rest of the function at x equal to 0 with rest of the function for x not equal to 0, because splitting this up means that f of x equal to 0 is actually 0. Okay, so before I go ahead, let me sort of give you evidence that this large deviation form is not something that I simply cooked up. It actually, you can see this in numerical calculations quite clearly. So if this is the form, what I have done here is I have taken g of rt, divided it by nr, and then plotted, divided also by g of r 0 comma t, so that all the curves basically start at the same point. I take a log and divide by L, and you can't really see here, but all these different symbols or plot markers for different system sizes really are on top of each other for all, for a sort of reasonably large range of time. It also happens no matter, it happens across parameter ranges. So we did this numerics on a non-integrable flow case spin chain, which actually has an MBL transition, but in this case we stayed sort of on the ergodic side of the transition. So, however, what we have so far established is that this function is indeed a function of x, because see, here I've scaled things by r over L. We still don't know what this function is. But the nice thing is that we don't actually need to know this, because of the large deviation form, the physics is actually controlled by the saddle point of the exponent. And because, let me go back, because this function has, or the number of states at distance r, the nx function is simply x minus half whole squared, I get the saddle point equation, which is of this form. And then the conservation of probability, I need to calculate, this should be satisfied, yields a relation between g of t and the function f of xt at the saddle point. Now, remember that the saddle point actually depends on time itself. Okay, so now now that we have understood that how to actually work with the saddle point, we trivially go and compute the fact that the spin autocorrelation is simply given by 1 minus 2 times the saddle point, which is actually given by this expression, and the return probability, which is nothing but e to the power minus L times g of t, that actually, or once you identify it with, once you write down the relation between g of t and f of x star comma t, which I'm not writing because it's ugly, you can write down the approach of the return probability to its infinite time value, again in terms of the saddle point and the behavior of the function f at the saddle point. Okay, so that's kind of the mathematical algebra that goes in. But the point is, we are interested at very long times where c of t is very small and r of t is going to approach its saturation value. Now, it's not a bad approximation to say that as time gets larger and larger, this propagator g of r comma t becomes more and more uniform on the Hilbert space graph. That means that the dependence on x should begin to go away, and that's possible if f of xt goes to 0. You can say that it can go to a constant, but the constant will basically get absorbed in g of t and will go away in the normalization. So f of xt actually goes towards 0. At the same time, notice that c of t is also equal to the derivative of the function at the saddle point. And we know that c of t also should go towards 0 if I'm in the ergodic phase. So both f of x star comma t and the derivative at x star, both of them should go to 0 as t goes to infinity. So the final sort of piece of information that we need is how do they go to 0 as t becomes very large relative to each other? And sort of a reasonable assumption or a conjecture, and I'll sort of justify this conjecture, is to say that they go to 0 together as a power law of each other. And once you do that, you end up with a relation between the approach of the return probability to its infinite time value as or a relation between the return probability's approach to its infinite time value and the autocorrelation, which is basically this main sort of result of the work. Now, the point is, I said that this f of x star comma t and the derivative, they go to 0 as a power law. And in order to check that, we actually again went back to our non-integrable flow K model, and we tried to compute the saddle point. That was a bit of a messy numerics because it's not easy to calculate the saddle point because we only have order L points on the propagator. So we have to make sure that whatever interpolation we do, whichever numerical scheme we use to compute the saddle point, that's more or less robust. All of this leads to reasonably large error bars and large spreads in the data. But nevertheless, you can see that, I've plotted f of x star comma t and its derivative at x star on double logarithmic scales. And you can see that they more or less fall on a straight line for large enough times. So, and this slope also seems to be independent of the different system sizes that we consider. So that gives sort of some credence to saying that indeed f of x star comma t does go as a power of the derivative at x star, which means f of x star comma t goes as some power of the spin autocorrelation. So if I put all that together, I basically get to this relation, which is quite a simple relation at the end of all this circus, that the approach of the return probability is indeed simply a power law of the autocorrelation. Now, what are the implications of this? Fine. This is a possibly a nice result. Now, the implications are, are the following. So suppose I actually take a model which has no conservation laws. By the way, I should mention that in everything that I did, I didn't actually use the fact that whether there are conservation laws or not. So we have checked it for models with both conservation laws and models which do not have any conservation laws, and sort of everything goes through. So if I have a model with no conservation laws, then you expect the spin autocorrelation to decay as an exponential or a stressed exponential in this slow dynamics phase. So if I use this relation and I say that C of t is actually a stretched exponent, then what we find is that the return probability approaches its infinite time value also as a stretched exponent with the stretching exponent, which is the same as that for the autocorrelation. What changes is that the effective time scale gets rescaled, but it remains a stretched exponent with the same stretching exponent. Okay? On the other hand, if I go to a model with some conservation law, say it has some U1 conservation, say magnetization is conserved or sigma z is conserved, total sigma z is conserved, and I'm looking at the sigma z autocorrelation such that C of t goes as t to the power -1 over z, z being some dynamical exponent, then again what we find, if I plug this into this expression here, is that the return probability approaches its infinite time value again as an anomalous power law. And that power law, of course, is different. It's basically alpha over z, where alpha was this power that was relating how f of t and its derivative went to 0 simultaneously. So the key point of all of this is that the approach of return probability to its saturation sort of unambiguously encodes the decay of the spin autocorrelation. And once we have an analytic way of calculating this return probability, which we think we will have in the near future, we can actually make some predictions about the spin autocorrelation. Okay? So I'm almost done. Let me sort of conclude. So I basically set out to build some connection between real space dynamics and the dynamics on the Hilbert space. So in particular, I took the real space autocorrelation and the Hilbert space return probability, and I could sort of construct an explicit analytic relation between them, which is here. And one of the implications was that if you have a model with no conservation laws, you end up with both of these quantities behaving as stretched exponents. If you have a system with conservation law such that things decay as, and I mean, in a model with conservation laws, both of them tend to decay with the anomalous power laws. Okay, and I should say one thing here, that all of what I said is actually true for the average spin autocorrelation. Now, it will be, I mean, we have not yet looked at how to take the typical values of the spin autocorrelations and connect them to possible Hilbert space correlations. And that's actually important to do, because if it is really true that things really are governed by rare regions and Griffith's effects, then you expect the mean and the typical to behave very differently. And so that's an important piece of work that at least needs to be done. Beyond that, as I said, in terms of work in progress, we are sort of trying to come up with an analytical way of computing the return probability based on dynamics and localization of single particle on high dimensional graphs. The sort of next step would be to actually think about something more complicated than the 2-point correlation. So the autocorrelation, I could relate to something on the Hilbert space, which basically was also a 2-point correlator on the Hilbert space, right? Because this G of r comma t that I wrote, that actually involves only effectively involves only 2 states on the Hilbert space. But in one of my recent works, I showed that if you allow for higher point correlations on the Hilbert space, you can actually calculate or relate them to the entanglement of a given state. So another thing that we are doing right now is to extend those 4-point correlations to their dynamical versions so that we can understand the entanglement dynamics from the viewpoint of the wave packet dynamics on the Hilbert space graph. And maybe you can understand some of the more interesting stuff there, such as the logarithmic growth of entanglement in MBL phases. So I think with that, I'll stop with pointing towards the reference one last time, and also Vikram has a poster. So if there are any questions that are still there, please go and ask him in the poster. Yeah, with that, I'll thank you for your attention.
Okay, we have time for some questions.
Yeah, so where exactly did you use the fact that your system was ergodic?
Oh, I used the fact that the system was ergodic here. Here. So I said that as t becomes very large, this g of rt should become uniform on an average should become uniform on the entire Hilbert space graph, and also the derivative should go to 0 because the derivative is equal to the spin autocorrelation. So the spin autocorrelation should also go to 0. That wouldn't happen in an ergodic phase. So you can do this for the MBL phase also. In the MBL phase, I don't know what happens very close to the transition, but in the MBL phase, these things will not happen. The dynamics is not that interesting. It's a steady state, or not, I shouldn't say the steady state, but the fact that C of t remains finite, but you can actually write down exactly the same expressions. And once you put down the fact that f of x comma t in the limit of t going to infinity has some non-trivial profile, you can extract what the infinite time autocorrelation will be from this. It's actually a very trivial exercise.
Okay. Further questions?
So for the initial state, it still bothers me a little bit because if the initial states are superpositions and everything, then the return probability can be related. Is the
initial states are
is the superpositions of all bases or eigenstates?
No. Okay, then of course, if your initial state is a superposition of all basis states, then you anyway have like completely spread out on the.
Yes.
So then
that would actually be the spectral form factor, actually.
Yeah. Okay. So
there would be some rules where if you
but okay. So for the spectral form factor, that's not okay. If you want to relate the spectral form factor to Hilbert space correlations, that's not the right way to do it. One of the ways in which you can do it is to compute autocorrelations for all possible operators. But computing autocorrelations for all possible operators means that you actually, for each operator, you have to go to a different basis for the Hilbert space correlations. Because see, the point is here, I'm trying to relate the autocorrelation of the sigma z operators. So that's why I wrote down the Hilbert space basis in terms of the sigma z product states.
Yeah,
and that's why I could do that.
I think I agree with you. I'm just saying there's some dependence on the initial states.
I mean, yeah, I mean, as far as they are product states in sigma z.
Okay, yeah, that I agree. And another question that I have is, for these kind of quantities, I'm guessing, I expect that the difference, you comment on the difference between the system without any conserved quantities and with conserved quantities. And I'm guessing that in the fully chaotic case, the difference between these two subcases and near MBL or pre-thermal MBL, the difference between two cases, there should be some differences. Do you see that?
Of course, I mean, if you are very, very ergodic, then if you have a conservation law, then you should see diffusion. Whereas in a model without any conservation law, things should simply decay exponentially in space.
And how does it change as you go near?
I don't know. I mean, Sarang, I think, is the right person to ask this question.
Okay.
Close to the transition.
Thank you.
Okay.
The calculation for G of R that you were doing, would it be right to say that it's a calculation of a random walk on a hypercube? It's a property of that random walk.
It's a property of the random walk, except it's not just a single walker that's walking.
Oh, when?
Because because at any time the state is a superposition of. It's more like you can think of this as some fluid flowing through the. It's not just a thing, because at any point in time, the state is actually a superposition of all of these basis states.
But where does that enter the calculation?
Oh, it enters the calculation because, see, if it were a random walk, then at any point in time, my g of r comma t would be peaked at a specific value of r. Because, the random walker would be at distance r. But
well, no, I don't think that's necessarily true. Does that mean it would be some sphere, so to speak, as it spreads out? I mean, you mean in a particular realization of the random walk?
Yeah, in a particular.
You're talking about the probability distribution of the random walk.
No. So I'm talking about the single realization. But here, in a single realization, it's the wave function that completely spreads out.
So okay, so this is a property of the probability distribution of the random walk.
It's a property of the probability distribution of the random walk. Yeah. So we tried doing this. The difficulty is that there are terms which contain the coherences of the unitary dynamics. So that's something that's not in the random walk picture. So I cannot write down an effective classical master equation on the hypercube because I need to worry about terms like Ci star Cj. It's not there in the random.
Where do those terms enter in?
Oh, those terms enter when I define this, when I define this propagator. So it's not this propagator, sorry, this propagator. So because what I am doing is I am so this is basically the probability of, so when j is not equal to I, that will give you the off diagonal element in the density matrix at a particular time.
Yeah, I guess it's a question now.
Yeah, it's a quantum random. Yeah.
Well, yeah, but that's
No, I think that's probably the best way to put it, that it's the square of an amplitude. But the thing is that it's a square of an amplitude, but what I need to evolve are not the squares of the amplitudes, but the amplitudes themselves.
So you're not saying it's a free particle propagator on a hypercube.
It's not a free particle in that sense. It's a single fictitious particle on the hypercube, which has its own quantum mechanical evolution, which is governed by the representation of my dynamics on the Hilbert space. I mean, that basically, of course, if I write down the Hamiltonian, so suppose it's not a flow case system and it's a Hamiltonian, then of course the Hamiltonian looks like a tight binding model on the Hilbert space graph, and that's it. Except that the matrix elements are correlated and so on. So it's not. Also, in the calculation, what we do is we just, okay, so in the calculation, we never actually compute these, in the analytic calculations, we never compute this explicitly. We actually say that it has this form, which has a large deviation form, and then we just worry about the saddle point. So,
Okay, one more question.
So if you take not the MBL integral phase, but just like free fermions or something, then this should still decay, right? I mean, as z equal to 1, and so there it works like, I mean, like probably you can compute exactly, right?
Yeah, there you can compute it exactly.
And it works like.
Yeah, I mean, there, of course, there, the thing is that, of course, you can compute it. Oh, you mean like completely free, like no interactions either? So we didn't actually try it there. Of course, you have to put many particles so that your Hilbert space graph is large enough, but there's no reason why it should not work.
It should still work.
It should still work, because I didn't make any approximations about
equal to 1, and then
I should get z equal to 1.
You will get
Or in the simplest way to see this is that suppose you put just one particle, then the Hilbert space graph is nothing but the real space graph, and then it will obviously work.
Okay, with that, let's thank Sthitadhi and Yuto for their nice presentations.